the exhaust pipe still available. So hopefully we can provide enough heat transfer energy that required to evaporate the ethanol. And the work is, for there will be go through the copper tube, and hopefully when they come out from the end of the copper tube, it's already hot enough and has enough heat transfer energy. The dimension of the exhaust pipe for the inner diameter is same with that one, is 0.0762 meter, and for the outer diameter is 0.0889 meter. Meanwhile, for the copper tube, the inner diameter is 0.08 meter, and the outer diameter is 0.015 meter. And now, after that, we need to calculate the heat transfer energy. We can use this equation where the temperature difference divided by the total thermal resistance. The difference between the first design and this design is the total thermal resistance F4 parameter, the inside thermal resistance, the inside wall thermal resistance, and then the outside wall thermal resistance and outside thermal resistance. The inside thermal resistance and inside wall thermal resistance is for the exhaust pipe, and meanwhile for the copper tube is outside wall thermal resistance and outside thermal resistance. And then we need to calculate the thermal resistance. It can be found by using this equation where H is the heat transfer coefficient and A is the surface area. But before we can find the heat transfer coefficient, first we need to find the Nusselt number. To determine the Nusselt number, first we need to calculate the Reynolds number, because from the Reynolds number we can know which equation that will be used and what flow that goes through inside the copper tube. The Reynolds number can be found by times characteristic length with velocity and divided with kinematic viscosity. The characteristic length is equal to inside diameter of each part, and the velocity can be found by divided volume flow rate with the area. And for the volume flow rate, we can find it from divided mass flow rate with the density. And for the mass flow rate, we can find it from the engine baseline data test and from the engine specification data. From the calculation, we found that the Reynolds number is greater than 10,000. So we can say that the flow is fully developed turbulent. So we can use this Boole equation. And the value depends on the purpose, 0.3 for cooling and 0.4 for heating. And for the inside pipe, we use 0.4 because we want to heat up the outside pipe. And for the outside pipe, we will use the 0.3 because we want to cooling down the inside pipe. After that, we need to calculate the wall thermal resistance using this equation where K is the thermal conductivity of each material. For the outside pipe is copper, and for the inside pipe is stainless steel. And after that, we can find the heat transfer energy using the bottom equation. But what we find is that since we divided the heat exchanger into several segments, the heat transfer energy that we calculate is only at the first segment, and we need to find the heat transfer energy or KI at the second segment, like Awan already explained before. And we can find it by dividing delta Ti with the total thermal resistance. The value of total thermal resistance is still the same, but the Ti is different. The Ti can be found by T3 minus T4. And then since the heat transfer energy is the same for both pipes, so we can use the number 2 and number 3 equation and rearrange it, and we can find the T3 and T4. After we find the T3 and